Hello, today I will talk you through building an automated deep learning intrusion detection system. So in this project, we're overviewing an artificial intelligence model that acts like an automated digital security guard for computer networks. By training a neural network on real-world network flow data from the CIC-IDS2017 benchmark dataset, we can automatically separate harmless routine network traffic from malicious cyber attacks in real time, helping modern security operations centers keep up with modern threats. Security teams today are struggling under an unprecedented volume of network data and security alerts. So the objective with this project is to improve modern deep learning models. The objective of this project is to prove that modern deep learning models can serve as a reliable first line of defense, automatically classifying network connections with high accuracy so humans security analysts can focus on critical threats rather than wasting time on false alarms. This project is urgent because every single second a modern enterprise handles millions of tiny network traffic packets. Traditional networks rely on rule-based intrusion detection systems. Think of them like strict checklists that look for known bad behavior. The big problem is that these legacy systems produce thousands of false alerts every day, and they miss brand new novel attack techniques that aren't on their checklist. So to solve this, we use Keras to build a deep neural network. Instead of relying on rigid pre-written rules, the neural network learns complex patterns directly from network flow behaviors, allowing it to accurately flag intrusions while keeping false alarms to a minimum. So before you can train an AI model, you need high-quality data. So we use the CIC-IDS2017 dataset, which contains over 2.8 million real-world network traffic logs, including diverse cyber attacks like denial of service, port scans, and brute force attempts. As you can see, in the table, raw security data is messy. It contains infinite numbers, missing data, and duplicate records. So during our data hygiene phase, we cleaned out invalid data, mapped all the different attacks categories into a clean binary target. And we'll review more of that later. Just to review the code here, you can see uploading the data and cleaning the, or uploading the data and reviewing what kind of information exists inside of the files. So this is our data end-to-end pipeline. So we pull in raw flow metrics, remove corrupted values, and drop unhelpful columns like duplicate sessions. We convert textual labels into numerical output 0, 1 so that the neural network can process them. And then network metrics like duration and packet counts vary widely from 1 to hundreds of thousands, so we use standard scale to normalize everything to a zero mean scale, ensuring that large numbers don't overwhelm smaller ones when the neural network does its internal math. We then strictly separated 80% of our clean data set for model training and held back 20% of the unseen in order to validate our final test accuracy. We first cleaned the data. This just explains more about the reasoning behind each step, and why it needs to be done. But just for the sake of time, I won't read through all of it. But just as an example, to go over one fundamental concept, we need to split the data set into 80% training and 20% testing because it simulates a real-world scenario, ensuring that the model can reliably detect brand new cyber threats in normal traffic flows and not just memorizing the training examples. Okay. So next we'll go into how we built the neural network. So we chose a streamlined MLP architecture built with 3 main layers. The first hidden layer consists of 16 neurons with RAID-low activation. This layer ingests all numerical flow features and discovers fundamental relationships between packet timings and sizes. Then we have the second hidden layer, which consists of 8 neurons, also using RAID-low. It compresses those feature relationships into higher level threat concepts. And then we have a single final neuron using a sigmoid activation function as our outer layer, and this converts the model's internal math into a clean confident percentage between 0 and 100%, indicating whether a connection is malicious. So again, just to review more of the under reasonings why just the concepts behind the neural network. I won't go read through it because again, just for the sake of time. But yeah, you can see here the code here for building the neural network. We have the 16, 8, and then the 1 using sigmoid and ReLU. Okay. So we trained the network over 20 epochs with a batch size of 256 utilizing the atom optimizer and binary cross-entropy loss. The result is that we achieved an extraordinary 99.4% overall test accuracy. And because we used normalized inputs and a conservative layer size, the network converged smoothly within the first few training cycles without overfitting or memorizing the training data, and actually learned to generalizable patterns of cyber threats. Accuracy alone doesn't tell the whole story. You have to evaluate precision and recall. So looking at the numbers on a test set of over 46,000 unseen samples, precision is 99%. Out of all connections flagged as attack, false alarms for analysts. Then recall is 98%. The model successfully caught 98% of all intrusion attempts hidden in test traffic. Then F1 is 0.98, demonstrating excellent stable balance. Out of the 419,000 benign traffic flows, only 918 were wrongly flagged a false positive rate of just 0.24%. So how does this work? How does this relate to practical decision making? The network outputs a probability score P. By default, any flow with a probability of 0.5 or higher is categorized as an attack. However, in real-world security operations, false negatives are far more dangerous than false positives. If a system flags safe traffic as an attack, an analyst spends a few minutes verifying it, but if a system misses a real attack, your database gets compromised. Knowing that our model's strong 90% recall rate provides severe risk mitigation for enterprise networks. The strengths of our system is that it processes thousands of flows per second, requires no manual rule maintenance, and keeps false alarms extremely low. Limitations and accepts, well, like most cybersecurity data sets, rare attack types make up small fractions of the data, so in order to, it would be good to include more of those. So in conclusion, what is the ultimate value of this deep learning system? Well, it empowers human security analysts by automating triage with high precision. Security teams are liberated from alert overload. So this model can easily feed directly into existing systems and instantly block malicious IPs in the moment and flag the high probability score. So thank you very much. That's everything.